columns and their tendency to buckle when subjected to an axial compressive force. Now, if you remember back at the beginning of the course, we talked about normal stress, and we calculated normal stress as being equal to the applied load over the cross-sectional area. Now those videos, if you notice, the problem was always set up so that the member was in tension, and that's because if you slowly increase that applied load in tension to the point where you get the material yielding, we're going to find out what that what that yield stress is. And from yield stress, what you do is you apply your factor of safety, and then you're given your allowable stress, which is basically just the stress that the maximum stress that we're going to let the member be subjected to, and we're not going to be concerned about it yielding at all. Now, in compression, even if the normal stress is less than the allowable stress, it's possible for a column to buckle, basically having a rapid change in shape, something like that, if its equilibrium is disturbed. So equilibrium can be disturbed, by the tiniest of environmental conditions or anything but an absolutely perfect alignment of the column as built, or even a slight imperfection in the material or something like that. But not just any axial compressive load will make a column buckle. Imagine if you just grab your pencil and you push on both ends towards the middle, you're putting it into compression, but it's not buckling under that load. If you put like way more force, try to support a bookshelf or something fully loaded with your pencil, then you're going to be getting buckling. So there's a point somewhere that we're crossing with the applied load that we call it P critical. It's the critical applied load, and the expression to find out what that is, basically this is the load that the column will be able to buckle at. This is just equal to pi squared times EI over L squared. Alright, so the material properties, it depends on the actual column, right? E is a material property. Moment of inertia is dependent on the actual cross-section of the column. And L squared here also depends on the actual column we're looking at. So if P is less than P crit, no buckling will occur. And if P is greater than or equal to P crit, buckling will occur. So this expression here that we have for P critical is called Euler's formula. And what we want to do with that is we want to rework it a little bit to go from P critical to the critical stress. So we'll write critical stress. So if we have stress is equal to P over A, then the critical stress is just going to be equal to P crit, the critical load there, over the cross-sectional area. So we already have the expression here for P critical. So the critical stress is just equal to that, pi squared EI over AL squared. And if you remember, another way that we can write I here, the moment of inertia, is I is equal to AR squared. So A is the cross-sectional area, and R is the radius of gyration. So we can substitute that in. The A is going to cancel with the one on the bottom there, so we're going to have pi squared E R squared over L squared. Now, the way that I would rework this is, or we can reorganize this a little bit, so just not leaving anything out, we have pi squared E. This is the same thing as multiplying that by R squared over L squared. And then we can also write this as pi squared E divided by the inverse of this. So pi squared E, this is equal to pi squared E divided by L squared over R squared. And that can also be written as, maybe let's come down here. So this is the critical stress is equal to, we'll just bring the square out there, so it's pi squared E over L over R squared. Now this L over R here is what we call the slenderness ratio. Basically, if a column, the more slender a column is, the bigger this number will be, and then the smaller critical stress will be able to support without buckling. Now, If the column is not circular or square, so like a rectangle or an I-beam, it's going to have one short axis, and that is the direction that the column is going to buckle in under eccentric compressive load like this. So in those cases, you'll have more than one radius of gyration, so we want to select the smallest one for that given cross section. Now in a square, the radius of gyration is going to be the same in both directions, and so the column could equally buckle in either of those two directions. And for a circular column, there's the radius of gyration, there's just one, and so it can actually just buckle in any direction. So that's just stuff to think about. Critical stress, as we've written it here, is proportional to the modulus of elasticity and inversely proportional to the square of the slenderness ratio. So again, just basically a long, slender column will be more likely to buckle than a short, stubby one, and that makes sense intuitively. So anyways, that's just an introduction to column buckling. We haven't considered safety factors in these expressions yet, so we're going to come back to that later in a couple of videos, or also if we haven't really done the analysis yet of how to tell whether or not a column will buckle first and before it yields, or if a column would yield before it buckles. So we'll get into that stuff in future videos. And in these expressions here, we're also, in future videos, we're going to replace L here, length, with effective length, because there's different types of columns that can have different end connections. But
length for columns with different end conditions, because in the last video we only looked at a two-dimensional column that was pinned on both sides, and when we had that, we said that our P critical, that critical load that would pretty much cause it to buckle, is equal to pi, that was pi squared EI over L squared. Now when we have something like this, double pin connection in a column, it's free to bend basically all the way from pin to pin, so you're going to end up getting some sort of deflection, probably like that. Now if we applied the same point load here on a member that is fixed on one end and free at the other, then it's not going to deflect the same way. Basically it's going to go something like that. Alright, and similarly if we're looking at one that has a column that has a pin on one end and a fixed connection on the other, it's going to be different. And also if we have a fixed connection on one end and two fixed connections, basically it's going to also deflect differently. So in the case of two fixed connections, because even after a deflection the rigid connections stay rigid, we're going to be getting something, this is super exaggerated, but it's going to come out straight like that, and then something like that. There'll be a curve in the middle and it'll come back in straight. And then same thing on that, if we have a fixed connection on one end, it's going to come out straight like that, but then this pin up here is free to just deflect right at the pin. So we're going to end up with some wildly exaggerated deflection just like that. And the way that we account for these is we have to talk about effective length rather than just the actual length of the column. So effective length, what we should really be writing this equation as is with a subscript E here, saying this is the effective length. Now in the case of the pin-to-pin connection, we can even write this here, pin-pin, then our length here is going to be equal to the effective length, and that's why this expression here doesn't change at all if whether or not we're talking about effective length or just length, because it's the same when we have double pin. Now in the case where we have a fixed end along with a free end for a column, then really the effective length is actually going to be twice the length of the actual column, because this would you see this curvature up here. Basically if you just continued it into the ground, it looks something like that, and it forms that curvature. And so we can write here that if this is L of the column, then LE is equal to, so LE is this, is equal to 2L. Now without deriving all of these numbers, for the case where we have a column that is fixed on both ends, so it's a fix, then basically its effective length here is just going to be LE is going to be equal to 0.5 L. And in the case where we have a a fixed end in conjunction there with a pin end, then the effective length that we're going to be working with is going to be LE is equal to 0.7 L. So really the only modification that you have to add into this expression here is just making sure that you're using LE rather than just the length. And it's pretty simple. You just apply the factor, whether it's a factor of 1, 2, 0.7, or 0.5. And then pretty easily from there you can calculate the critical load for your column. Same thing goes for the other expression that we had here for critical stress. So if we just write that in, that was pi squared E over LE. So just subbing in that LE over R squared. Again, in the previous video we were only looking at the pin-pin connection, so we just had L over R squared, but to be proper you should be using LE in place of L for those two expressions. Now there's one other thing to mention about this stuff is that these drawings here are in 2 dimensions, and these formulas apply to when you're just considering 1 dimension at a time basically. If you imagine, let's look at this first one here. If you imagined that this is a 3-dimensional problem, this hinge here is actually fixed to the ground, but these wheels here are not in a groove or anything, and this wall has 0 friction. It's like a super icy wall or something like that. Well, side to side, it's a pin-to-pin connection. But if you imagine it swinging in or out of the page, then down here it would be considered a rigid connection, because if you tried to imagine if you just grabbed up here and pulled towards you, that hinge is going to resist that as a fixed connection would. But basically how the problem would then see it for the determination of the critical load would be that this would be a fixed connection at the bottom and free at the top. If there's no friction there preventing it from going into or out of the page, then we'd be dealing with 2 different effective lengths, one for it buckling this way and one for it buckling into and out of the page. And then if this is a rectangular beam or like an I-beam or something that has 2 different radiuses of gyration, then you can't just say, oh, I'll select the one of this, I'll just select the smaller radius of gyration and throw it in here and find out the critical stress, or the smaller moment of inertia here and find out the critical stress, because depending on which way you look at it, the end conditions might be different, so we'd have to check using the different effective length for each possible direction that it's buckling in. So, column buckling, we basically just want to figure out what is the critical load and then what is our allowable load based on our factor of safety here. We want to check it against buckling. In this case, this column can buckle in 2 directions. We have to check both of those. Then we also want to make sure that it's not going to yield, the material won't yield before it buckles. So looking at this, we have a 3-dimensional column here. And we're talking about this as pinned joints, a pin on each end. So we'll basically treat these as ball and socket joints. So they are able to basically, this pin, it's like a pin in 360 degrees. But because this rectangular cross section has kind of 2 distinct ways it can buckle basically in the YZ plane. So sort of as we're looking, it's left, it can buckle from left to right or right to left, like that way. Or it can also buckle in the XZ plane, so basically going kind of into the page that way or kind of out of the page that way. So basically what we need to do is we need to first figure out what our effective length is. Now in both, considering both planes it can buckle in, it's considered to be pinned in both of those directions, so our effective length, no matter how we look at it, is going to be just the actual length of the column because it's that pin connection. Now that came from the previous videos where we're talking about different end connections, but in the next videos we'll do different examples. So for now, effective length is equal to the length where we have pin-pin connection on this column. Alright, the next thing that we need to do is we are going to be using this expression here that is, we're going to be looking for the P grit, the critical load that's going to basically be where the column is going to have the tendency to buckle, so that is equal to, that is pi squared EI over LE squared. So we need to figure out what the moment of inertia is, and because we have this rectangular cross section, we're gonna have to figure out 2 different moments of inertia depending on which way we're thinking about this column buckling. So For the moment, we're going to use, we can calculate, let's calculate it up here. So for, let's do it down here. I'm really indecisive right now. So for Iy, basically the moment of inertia about the y-axis here, this is going to be equal to 1/12 times b times a cubed, right? Because when we're looking at this about the y-axis, this a, if we normally think about this as 1/12 base height cubed, this a kind of becomes our height. So we can plug in the values and we get 0.0267 times 10 to the negative 6 meters 4. And then we can also find the moment of inertia about the x-axis, which is what we're going to be using for buckling in the xz plane. And we find that to be equal to 0.1067 times 10 to the negative 6 meters 4. So now we have everything we need to find the critical load in buckling in each plane, basically in the yz plane and the xz plane. So let's go and plug those in. So we have P crit. Let's consider buckling in the YZ plane first, and again YZ basically could buckle that way or it could buckle that way. So we just need to sub in that we have pi squared E, and in this case we're using Iy, right, the moment of inertia about the y-axis, and then this is over LE squared. So if we just plug that in, we're going to find that in the YZ plane that P crit is equal to 5.9 kilonewtons. Then when we check for P critical in the XZ plane, we're going to have to basically just redo this expression. So we have P crit in the XZ plane, and that's just going to be equal to pi squared EI, and this is with the subscript x because we're looking at the moment of inertia about the x-axis now, and this is over LE squared. So we're just going to find that that is equal to 23.4 kilonewtons. And now what we want to do is we just compare the two different critical loads. So we have, for buckling in the YZ plane, the critical load is 5.9 kilonewtons. And for buckling in the XZ plane, our critical load is 23.4 kilonewtons. And intuitively this makes sense. The skinny, basically we're saying that we need a smaller load here to make a buckle in the direction that has basically a smaller amount of material basically around that axis. So if we applied, let's say 6 kilonewtons, then we will have crossed this threshold and we're most likely going to be getting buckling. So 5.9 kilonewtons is the value that we have to take for P critical for the whole column. Now, if we want to use that, we can figure our allowable load if we set our factor of safety up here as 2.5. So basically, we can just say that if you remember, the factor of safety is equal to the ultimate load over the allowable load. And if our ultimate load for buckling is 5.9 kilonewtons, then all we have to do for allowable load is that's going to be equal to 5.9 kilonewtons over 2.5. I'll write that a little bit cleaner, 2.5. So our allowable load for buckling with this factor of safety of 2.5 is going to be 2.36 kilonewtons. So that's something to watch out with these problems, is typically you're always going to have to check for buckling in two directions and then take the smaller value, and then if you're talking about factor of safety, like maybe your professor's only asking for you to calculate P crit, but if you're looking for the actual allowable load, then take that factor of safety into consideration. The one other thing that we can check with a column problem is it's possible that the column buckles before it yields, or it's also possible that the column yields before it buckles. So if we want to just quickly check that this column won't yield before it buckles and that this is in fact our true allowable load, then what we just need to do is if we come back up to the top here, the yield stress was 250 megapascals for this particular material. So if we know that, let's just write this in. So we have yield stress is equal to 250 MPa. Now we know that stress is equal to force over area, right? So this is equal to the applied load over the area. Now our cross-sectional area is going to be, if we do that up here, we have area is going to be equal to base times height, basically the cross-sectional area. So 20 millimeters times 40 millimeters, that is 800 millimeters squared. So we'll bring that down. and we'll be basically just calculating for our yield load here, the load that will cause yielding. So just multiply area to that yield stress, and we're going to get this expression here where we have that yielding load is going, or the ultimate load basically, is going to be equal to 250 MPa times, and you know what, I like to write out the units like this, so 250 times 10 to the 6 newtons per meter squared times that area, which was 800 millimeters. That's also just 800 times 10 to the minus 6 meters squared, so those meters are going to cancel out. And the value that we're going to get is just 200,000 newtons. 200,000 newtons, which is equal to basically 200 kilonewtons. Alright, so if we take, this is our yield, this is our ultimate load. If we just check again using the same thing, factor of safety is equal to allowable over ultimate, then that means that our allowable load for yielding is going to be equal to just 200 kilonewtons divided by 2.5, and that is going to give us a value of 80 kilonewtons. So we're definitely going to buckle before that. If we apply 5.9 kilonewtons, then we're most likely going to buckle. And that's that's important to look at, because if you look at this column, it is quite long, right? It is 3 meters long, and it's very slender. So it's a very slender column, and very slender columns are very prone to buckling. So in this case, it will definitely it will buckle in the YZ plane. On column buckling, in this case we have a three-dimensional column that has a fixed connection at both ends. So very similar to the last video. If you watched it, we had basically this exact same problem, only it was pinned with ball and socket joints at each end. This time we're talking about fixed ends, and that's going to change our effective length that we're dealing with. Now if you remember from a couple videos ago, we had been talking about this stuff, or different situations where we had like pin, fixed end, and free end, a fixed end with a pin end, and a fixed end with a fixed end. Well, this is the situation that we have here in this video. So we're saying that that means that our effective length is going to be equal to 0.5 times the actual length. And so in this case, our actual length is 3 meters, and so our effective length, maybe let's not draw an equal sign, let's draw an arrow. So we have our effective length is going to be equal to 0.5 L, so that's 1.5 meters. Alright, and that is coming directly from that last, not that last video, but a couple videos ago where we talked about that. Okay, so when we start talking about this for buckling, this column can, as a rectangular column, it can buckle in two different directions or planes basically. It can buckle in the YZ plane, basically going out that way or coming this way, and it can buckle in the XZ plane, so basically kind of going into the page like that or out of the page like this. So we need to check what the critical load is for each possible direction it can buckle in, and then from there we can use the factor of safety to determine the allowable load, and then after we'll also check to make sure that this thing, to see if it's yielding before it's buckling or whatever. Alright, so the formula that we need to use, just like the last couple of videos, was P is equal to P crit is equal to pi squared EI over L E squared, right? The effective length squared. So in this case, we do need to identify the moment of inertia that we're going to be using in each direction. So for buckling in the YZ plane, just like the last video, we need to find the moment of inertia about the y-axis. And then for buckling in the XZ plane, so this way, we need to find the moment of inertia about the x-axis. And we did calculate those in the last video, so I'll just write them right here. And then we want to use each of these when we calculate for buckling in each of the planes. So let's take a look at buckling in the YZ plane first. So we want to figure out what the P critical is in order for that buckling to happen. So then we're going to have to use the subscript here for I, Y, moment of inertia about the y-axis when we're dealing with buckling going like that. All right, so when we have all of these values, we have the effective length, we have the moment of inertia, we have E, we have pi, obviously. So we're going to find that the P critical in the YZ direction is 23.4 kilonewtons. And now we want to repeat the process to find the critical load for buckling in the XZ axis. So let's throw in some subscripts here. XZ, and this time we need to be using the moment of inertia about the x-axis, so we have subscript x up here. Alright, so when we go and plug in all of those numbers, we're going to find that the critical load for buckling in the XZ axis is 93.6 kilonewtons. So now what we do is we select the smaller load as our actual critical load, because obviously if you surpass the smaller load to get up to the bigger load, you already would have buckled in that direction or in that plane. So what we do is we take this, and if we're asked to find the allowable load for buckling with some safety factor, we can do that. We just take our factor of safety, which is equal to the ultimate load over the allowable load. So we can just rearrange that so we get our allowable load is going to be equal to 23.4 kilonewtons over a factor of safety, which is 2.5. Alright, and that works out to be 9.36 kilonewtons. So with a factor of safety of 2.5, then we can safely support this compressive load here of 9.36 kilonewtons. Now, something that we should do is just exactly like we talked about in the last video, is we should check that that we're not at risk of yielding with this applied load. So let's just give ourselves a little bit more space down here. We know that the yield stress for this material in this problem is 250 megapascals, and we also know that stress is equal to force divided by area. So we have P over A, and in this case for yield stress, that is our ultimate strength, or our ultimate load here. So we can say Py or P ultimate, whatever. It's a load that's going to make the material yield. So what we do is we just have to rearrange this to solve for Py. So we know that the area up here, the cross-sectional area, is 800 millimeters squared. So we get 250 times 10 to the 6 newtons per meter squared. That's megapascals, times our area, which is just 800 times 10 to the negative 6 meters squared, and that's going to be equal to 200,000 newtons, which is 200 kilonewtons. And basically this material, when we look at this material will yield when we apply 200 kilonewtons to this exact column, and that's way more than if we applied only 23.4 and it's going to buckle. So it's safe to say that this column will buckle in the YZ direction. Number 3 for column buckling. In this case, we have a column with one fixed end and one free end. In this case, our column is not rectangular like the last two examples. We're dealing with a W shape, which basically stands for wide flange shape. And the name of this wide flange shape is W360 by 44. You can look this up in the back of your Mechanics of Materials textbook, and basically any textbook will have tables for this sort of thing. And from there we can figure out, it just basically prints, it has all this information, it has all the moments of inertias in both directions, the cross-sectional area, the depth, the thickness, what else does it have? Radiuses of gyration. Basically everything you need to know about these columns is in the table, and so that's where these numbers come from for this wide flange shape. Alright, so when we're looking at this, this is we have one fixed end and one free end. So if you remember from a couple of videos ago, we had these diagrams. Well, in the case where we have a fixed end and a free end, this is this guy, the effective length that we're going to be using in this expression for P critical is twice the actual length of the column. And we have to make sure that that's in both directions that this can possibly buckle in. So this column can buckle in the YZ plane, basically going out that way or coming this way. And it can also buckle in the XZ plane, so basically going kind of into the page that way or out of the page this way. No matter which way we look at it, both of those are considered to be fixed and free. So we are going to use the effective length of 2L for both of our calculations. So let's maybe put this here. So we have LE is going to be equal to 2L. So the effective length that we're dealing with is 6 meters. Alright, so let's go and grab this expression up here. Alright, and let's start our calculations. We can calculate for buckling in the YZ plane first. So what we want to do is just drop this in here. Let's put in some subscripts. So we have, for calculating for the P critical that would cause buckling in the YZ plane, let's give it that YZ. And in that case, we're looking at the moment of inertia about the y-axis here. So we need to give it that subscript, right? Because if we're looking at buckling this way, basically if this is the top-down view, it's going to be going out that way. So we're looking for that moment of inertia about the y-axis. Alright, so if we just plug in all those values for buckling in the YZ plane, we're going to find that it's 449 kilonewtons. And then we want to repeat this calculation for buckling in the XZ plane. So we'll just change our subscripts here, so we're looking for buckling for the P critical in the XZ plane. So that means we're going to be looking at using the moment of inertia about the x-axis here, so we'll give it that subscript. So if we go and plug all of that in, we're going to find that our P critical for buckling in the XZ plane is 6,689 kilonewtons. So the actual P critical for buckling in this case is going to be 449 kilonewtons, because obviously if we go all the way up to 6,000 to reach buckling in the XZ plane, we already will have buckled in the weaker plane, which is the YZ plane. Now, if we do want to maybe figure out what our allowable load is, if you're given a factor of safety, then all we have to do is we just say that our factor of safety is equal to our ultimate load over our allowable load. So in this case, all we have to do is switch those, and we're getting our allowable is going to be equal to our ultimate, which is in this case our P critical, so 449 kilonewtons, and we would just divide that by the factor of safety, so divide by 2.5, and that's going to give us an allowable load of 179.6 kilonewtons. So that is our that's our allowable load, P allowable. This was P crit, and there we go. Let's throw a box around that guy too. Oops, not a straight line. We want a box. Boom, like that. All right, so we found our actual P critical. We found our P allowable. One other thing that we should do is we should just check that this column is not going to not going to yield before it buckles. So all we have to do, it's pretty fast check there. So we just know that we have our yield stress. There we go. So our yield stress is equal to 250 megapascals, but the stress is also equal to force over area, and this is the force that is going to cause us to get yielding. So we that's what we're looking for here. So we have P is going to be equal to 250 megapascals, which is 250 times 10 to the 6 newtons per meter squared, times our area. Again, this area for this W360 by 44 wide flange shape comes from the tables in the back of your Mechanics of Materials textbook. So that is 5730 times 10 to the minus 6 meters squared, just that unit conversion right there. And that is going to give us 1,432 kilonewtons. Alright, so that is the actual force that's going to cause us to get yielding. Note that 1,432 is a lot bigger than 449, so we are going to be getting buckling before we get yielding. But if you're also curious just what the allowable, if for some reason if you want to know what the allowable force is for yielding, same thing, we would just divide this by our safety factor of 2.5, and that would give us a P allowable for yielding for 572.8, right? That's just that divided by 2.5. But clearly, the allowable force so we're safe from buckling is 179.6. So this one is going to govern, and we won't be able to apply anything more than that. 4 of column buckling. So in this example, we have a rectangular column that's fixed at one end and it's pinned at the other end, but this pin only works in one direction. Basically, it's for buckling in the YZ plane, the column sees this connection as a pin, but for buckling in the XZ plane, there's really nothing stopping it from swinging out if it was to buckle, so the column sees this as just being free to buckle in the XZ plane. So when we look at, if we go back to a couple videos ago, as always, we had these situations up here. So in the case of a fixed, let's do a fixed connection at the bottom and a pin at the other end, then the effective length that we're going to be using in our P critical formula is 0.7 times the actual length of that column. And then for a column that's fixed on one end and free at the other end, we're using effective length of 2 times the actual length. So depending on which way we're considering buckling to go in, we're going to have to use each of those. So maybe let's write those out. We'll just say that we have our effective length for the YZ plane. This is going to be where we have a fixed pin connection, so that will be equal to 0.7 L, and 0.7 times 3 there is just 2.1 meters. Alright, now our effective length that we're going to be using in the XZ plane is was 2L for the fixed and free connection, and so just 2 times, so we can write that 2L, so that's just going to be equal to 6 meters. Alright, let's go and grab this expression up here. We are going to need the moments of inertia about the x-axis and the y-axis, and we've already calculated those in previous videos for this exact cross-section, so I won't bore you with those. And we're just going to plug them into the P critical expression. So let's just give us, we have to do this for each possible direction for buckling. So let's check the YZ plane first, and that's going to give us the subscript IY, because it'll be buckling in this way or that way. So basically, from the top-down view, it's about the y-axis. There's the moment of inertia that we're concerned about. So when we plug all that in, we just get it to be equal to 12 kilonewtons. And now we just want to check for buckling in the XZ plane. So let's just bring this down here, and we'll add in our subscripts. So we're looking for P critical in the XZ plane, which means we're dealing with the moment of inertia about the x-axis. And then again, this is the effective length for the XZ plane. Alright, so when we just plug in all the values that we already have, we find that to be 5.9 kilonewtons. And 5.9 is smaller than 12, so when we look at this, the actual P critical that we're going to get for this column is 5.9 kilonewtons. We're going to be getting buckling in the XZ plane before we get buckling in the YZ plane. The other thing that we can do here is we can just check the allowable load if we want, based on the factor of safety. So let's just write it down here. We have factor of safety is equal to the ultimate load over the allowable load. So if we just rearrange for the allowable load, we will just get the ultimate load, which is 5.9 kilonewtons, divided by our factor of safety, which was 2.5. And that's going to give us an allowable load for this column of 2.95 kilonewtons. This is equal to P allowable. Alright, so let's throw a box around that one as well. That's our allowable load. And the last thing that we want to do here is we just want to check to make sure that the column doesn't yield before it buckles. We've been doing this in the previous videos, so all we do is we know that our yield stress is equal to basically just the force over area, and that force is the force that would cause this material to yield. So if we just rearrange for P, we're going to get our yield stress, which is 250, so we have 250 times 10 to the 6 newtons per meter squared, times 800, well this actually, I should write it up here, the area is equal to 20 times 40, so that's 800 millimeters squared. So in units of meter squared, that's just 800 times 10 to the minus 6 meters squared. So if you just multiply those two together, we're going to find that the force is 200,000 newtons, or in kilonewtons, that's just 200 kilonewtons. So 200 kilonewtons is way bigger than 5.9 kilonewtons, and it makes sense. This is an extremely slender column. When we're looking at this, it's only 2 centimeters by 4 centimeters in its cross-sectional area, or cross-sectional dimensions, and it's 3 meters long. So no wonder this thing is going to buckle. Number 5 for column buckling. In this case, we have some bracing that is going to impact the buckling in the YZ plane. So if we look at the effective lengths here, let's look at the effective length for the XZ plane first. It's going to be a little bit easier. If we look at it in the XZ, we have a ball and socket at each end and nothing preventing it from just bowing out like that if it was to buckle in that direction. So the effective length, we treat this as a pin-pin connection, and the effective length will just be equal to the length of the whole column, and that's going to be equal to 3 meters. Now if we look at the effective length for buckling in the YZ axis, it is impeded here. It can't just go out like that. It's going to hit that bracing and stop. So what we really do is if we were to see buckling in this axis, it would be something like that, where it can't move here, it's fixed in this part, so we're going to have bowing out like that, and then bowing out the other way down at the bottom there, or it could be the opposite. But when we look at this, if one of these sections is longer than the other, then that one is going to be the one of concern to us, but in this problem, they're each, the top half and the bottom half is each 1/2, so it's 1.5 meters. And basically what we do is we treat the, even if we call this, maybe we'll call the top half section A and the bottom half section B, then section A up here basically is just a column that is pinned on both ends, because it has a pin up here, and this type of bracing is, assuming it's frictionless and it's just preventing the motion there, then it's basically no different than a pin. So what we can do is we can even put another subscript here saying A or B, because they're the same length, and that's just going to be equal to the L, A or B, and so that's just going to be 1.5 meters. Alright, we will be needing to use this expression here for P critical for buckling in each of those directions, but before we do that, we're going to need the moment of inertia about the x-axis and the y-axis, so I'll just throw those up right here. And for buckling in the YZ plane, let's throw in the subscripts here. We're going to need the moment of inertia about the y-axis. And if we just throw in all the numbers now that we have here, even we can put in the subscript YZ for the effective length, we're going to find that the P critical is equal to 29.2 kilonewtons. And then we want to check again for buckling in the XZ axis. So if we throw in our subscripts here, we're going to have for XZ, we'll be using the moment of inertia about the x-axis. And then again the effective length for the XZ, buckling in the XZ plane. So if we do all of that, we just find that P critical is equal to 45.7 kilonewtons. So in this case, we look at them and we take the smaller of the two values, and that is going to be buckling in the YZ plane. So let's go and throw a box around that. It's going to be 29.2 kilonewtons, and that is going to be what causes us to get buckling, and that buckling is going to be in the YZ plane before it buckles. We would need almost twice as much, well, not quite, we would need more applied load for it to buckle in the XZ plane, but it's going to buckle first in that YZ plane. Alright, something else that we can do here is we can just find our allowable load if we're given a factor of safety. And so we have, all we have to do is just divide our ultimate load by the factor of safety. So let's write that. We have P allowable is this going to be 29.2 kilonewtons divided by 2.5, and that's going to give us 11.7 kilonewtons. So that is the allowable load that we can apply to be within our factor of safety here of 2.5. Now, as always, the one other thing that we want to check is this column going to yield before it buckles? And all we need to do there is we have the yield stress up here. It's 250 megapascals for this particular material. So we have sigma y is going to be equal to just the applied load over the cross-sectional area. And 20 millimeters times 50 millimeters, that's going to be 1,000 millimeters squared. So we can just rearrange this to find that load that's going to cause yielding. And we're going to get P is equal to 250 times 10 to the 6 newtons per meter squared times 1,000, so it's 1,000 millimeters, so that's 1,000 times 10 to the minus 6 meters squared, and that's going to give us 250,000 newtons, or just 250 kilonewtons. So clearly, if we're getting yielding at an applied load of 250 kilonewtons, but we're getting buckling at 29.2 kilonewtons, then yielding is not the concern, buckling is, and the allowable load that we'll be able to safely apply to this column is going to be determined by buckling in the YZ plane, and it is going to be a. And pure bending is what the middle of this beam between the two reactions here is going to be undergoing. So if we load a beam like this that's symmetrical with these equal loads on each end, then we're going to get a free body diagram that looks like this, where each of the reactions obviously has to be equal and opposite P here, and it's all symmetrical. So when we draw the free body diagram, and let's say if we started at the left-hand side, when we have shear in this section here from the end of the beam to the first reaction, but once we pass this reaction here, we're not going to be having any more shear here, because if we were to draw our free body diagram, we would have P pressing up. Somewhere over here we'd have P pressing down, and then for our shear force, V, it would just, shear would be equal to 0. So that's true for this whole section in here. So as far as the beam is concerned, all the middle section of the beam sees is just applied moments, and they would be going like this, because these force couples basically just exert an applied moment on the middle section just like that, and for all the middle section knows, that's what's going on. Now if we have applied moments like this, if we were to draw a little free body diagram with a virtual cut in it coming from the left hand side, we would have our applied moment, and then we would need an internal moment going like that to cancel that out. And if you remember from statics, this is the positive sense for an internal moment, so that would be positive. Or if we drew it from the other side where we took that cut, where we have a moment like that, when we have a moment on the left hand side going clockwise, that was also the positive sense for moments. And so when we have moments like this, that when we apply them, you imagine if you grab a ruler or something and you apply moments like that, it's going to sag down in the middle, or the concave side will be on the top. We call that a positive moment because it's giving us that positive internal moment. If we had the applied moments going down like this in the opposite direction, we would be getting a negative internal moment. So if we define the section here, the section that is in pure bending to have a length of L, then we know it's kind of obvious, like that when we talked about using bending a ruler, you know that it's going to want to have the tendency to bend down like this. So really, after we apply these moments, we're getting a final shape that looks something like this. But if we bend an object with actual depth like this, the top of this you can see actually that this line here is shorter than this line. And basically what we've done is we've taken an original length of L, and the top has compressed a little bit and the bottom has stretched out a little bit to get this final shape. Now if the top is shorter and the bottom is longer, that means that somewhere in the middle there has to be the exact length of L. And it turns out that for a rectangle, if this is a beam with a rectangular cross section, that line is right in the middle. So for a rectangle, like I said, it's exactly in the middle, halfway from the top, halfway from the bottom. But if we have different shapes that aren't symmetrical, we can get the neutral axis appearing either closer to one end or closer to the other end. But it doesn't matter exactly what the cross section is, whether it's a square or a trapezoid or a T shape or an I shape. If we're applying a moment like this so that we get a positive internal moment, then no matter where the neutral axis falls, if it's exactly halfway or if it's closer to one end or closer to the other, above the neutral axis we're going to be getting compression, and below the neutral axis we're going to be getting tension. And this is because the top half of the member, or the top part of the member here is compressing. It's getting shorter, so we're finishing here with lengths less than L. And down here it's elongating, so we're getting lengths that are greater than L. Now if we had a negative internal moment, then this would be flipped. We would have tension on the top and compression on the bottom. But compression and tension are really measurements of force or stress, and we're talking about changes in length. So if you think about what the expression for strain is, we have the displacement over the original length. Now, if you recall, we call this positive if it was in tension and negative if it was in compression. But really, what we want to do is we want to relate this into the force or the stress so we can actually confirm that, yeah, we're getting compression and tension. So we have Hooke's law, which was the normal axial stress is equal to the modulus of elasticity times the strain. So if we just rearrange that for strain, we get that's equal to stress over E. And stress, if you remember, is just a measurement of force over area. So we're getting P over AE basically. So by applying these moments on the end, we're actually creating strain by changing the deformations here by either shortening the member or lengthening the member. And when we do that, we induce an internal stress. So basically all you need to take from this is that when we have a positive internal moment caused by applied moments like this, that the normal stress and strain are going to be compressive above the neutral axis and tensile.
Conjugate beam example that is worthy and not always incorrect. But here we've got this cantilever beam that has an E that's constant, so you can say it's steel or something, right? And the moment of inertia of AB is 8 times 10 to the 6 millimeters to the fourth for 4 meters. And then it's the moment of inertia of segment BC is 4 times 10 to the 6. And we have this concentrated moment applied at NC. It's fixed at A. And what we'd like to do is calculate the displacement and slope at point C over here. And what we're going to do is we're going to apply the conjugate beam method for this. And the idea or the approach of the conjugate beam method is to do your real statics first, or statics on the real or given beam, and come up with a moment diagram, and then use EI to determine the curvature diagram. Once you have that, the curvature diagram, it's all about taking the real beam and drawing the conjugate beam and applying the curvature diagram as your loading, as your conjugate loading, and then using statics on the conjugate beam to determine the slope and the deflection right here. And that's the whole point of the conjugate beam method, is really to utilize statics principles to calculate slopes and deflections. And the idea is that if you calculate a shear in the conjugate beam, that corresponds with an actual slope in the real beam. And a moment in the conjugate beam corresponds with a deflection in the real beam. So here, let's go ahead and do it. So the first thing we want to do is apply our statics. So one is our basic statics on the real beam, statics on real right here. And this is simple. You know, calculating reactions here should be pretty straightforward here. So if I sum forces in the vertical, I would get AY is 0. If I sum forces in the horizontal, AX is 0. And my moment here, MA, if I sum moments about a point, is going to be equal to 500 Newton meters here. Okay, so really that one's a no-brainer, and hopefully you can see that. The next part to do is that moment diagram, and the moment diagram here is also pretty straightforward. If I have here, let's see, let me draw an axis here like this, and then let's give it some length about up to here, and let's go right about here. And so for my moment diagram here, in kilonewton, in Newton meters, right here, my moment diagram will simply just be constant all the way across, which makes it like so. And these are just 500 Newton meters, and this is my moment diagram. Okay, that's not too bad, hey? And then we want to draw our curvature diagram, and the curvature diagram just simply is dividing each point on the moment diagram by EI of the beam. So here, our curvature diagram, which will be M over EI diagram, okay? And so here, let's see, let me draw some lines, bam, bam, right here. My curvature diagram, if you look at it, let's see, I have a large moment of inertia here compared to segment BC. So you would expect your curvature to be less, okay? Because you have more resistance to bending here. So here I would have bam up to segment, whoa, segment BC here, right there, segment B right there. I have that, and this right here, this curvature would be 500 Newton meters divided by EI of AB, and then here for segment BC, I would anticipate that here, which it would probably be bigger because the curvature is going to be larger because the moment of inertia is less. This is 500 Newton meters divided by EI BC. And this is my curvature diagram for this beam. Okay. All right, there it is. Okay, and now that really is it in terms of statics. And statics is hard if you need more practice with moments, right? But here, let's go ahead and now the next thing we want to do is draw the conjugate beam. So 2 conjugate beam right here. And the thing about drawing a conjugate, this is really the hard part of this problem, is making sure you understand how the real boundary conditions translate into conjugate boundary conditions. And so here I have this beam, and if it's fixed in the real beam, then it's free in the conjugate beam. And I have a video on that, I believe, on how to calculate, how to draw a conjugate and a real beam here. And bam, right here. Okay, hopefully that looks relatively straight, although this line is not perfect. And boom. Okay, so here is, if you will, I'm going to call this A prime for my conjugate A, and my B prime and my C prime. And in my real beam, I'm fixed at A. So my conjugate beam, I'm free. I've got really no support or boundary condition at B. And then at C, it's free in the real beam. Therefore, it is fixed in the conjugate beam right here. Now, our loading. Our loading here is, if I have a positive curvature here, that load is going to act upwards. Okay, so here is one thing that you want to be aware of, and a mistake I make all the time here is that if I have a positive curvature diagram or positive moment diagram, then this right here is my bam, right here is my loading. My conjugate loading is upwards, and this right here is my 500 Newton meter over EI AB. Okay, and then same thing here for segment BC, because I have a positive curvature. I want this right here. This is going to be 500 Newton meters over EI BC. And what I need to do is calculate, now with my loading here, I want to calculate my shear and my moment at C prime. Okay, now this isn't necessarily the reaction. What you want to do is treat this like a cut just before the end here, right here, a cut just before the end, or just before you reach C prime right here. And so if I, keeping my rules of internal loading right here, my positive internal shear, if I make a cut and look on the left side, would be downwards like this, VC prime, and my positive internal moment here would be MC prime. Okay, all right, and I'm going to tell you what these positives mean, if we get positive or negative results, what that means in terms of displacement and our slope. Okay, and so now using statics on my conjugate beam, so statics on the conjugate beam. I want to determine that VC prime and my MC prime. So here, if I do sum of the forces in the vertical, I'll say this is equal to 0. Right here, I would get 500 Newton meter over EI AB plus 500 Newton meters over EI BC minus VC prime equals 0. And that tells me that VC prime Whoa, I almost made some big mistakes here. Don't forget the lengths. These are like distributed loads, right? So hopefully some of you were catching me as I made that mistake. This is 3 meters. So this should be a times 4 meters here, times 3 meters here. And that would tell me that VC prime is actually equal to 2,000 Newton meters over EIAB plus 1,500 Newton meters over EIBC. And I did the distances correctly. I'd use the 4 and 3 in the right order right here. And this right here is the same thing as the rotation or the slope at point C in the real beam, okay? All right, and I'm going to tell you in a second what this positive result means, okay? And so here, if I sum moments now about point C prime equal to 0, and I'll say this is positive right here, I would get MC prime minus 500 Newton meters over EIAB times 4 meters, which represents the resultant, times the arm, which is 3 plus 2 is 5 meters, minus 500 Newton meters over EIBC times 3 meters times 1.5 meters, which is the arm here. And that's equal to 0. And that tells me that MC prime is equal to, let's see, to 10,000 Newton meters cubed. And I messed up on units up there. Oh, damn, minus 2, right? So here, Newton meter squared up there for slope. Newton meter cubes over here, EIAB, plus, let's see, 5, blah, blah, that's going to be 2250 Newton meters cubed over EIBC. And this value here is the same as my deflection at C, okay? My deflection at point C here. Bam. And what this means, if you know we want to interpret some stuff, there are things you want to check all the time, or units, right? And so here, you know, I noticed that I made that mistake earlier, but the units of EI are Newton per millimeter squared times millimeters to the 4th, which gives me Newton millimeter squared. And I can convert this to meters, obviously, but the units will, it's just force times length squared, and the units are going to cancel out, and that leaves theta in dimensionless or in units of radians, okay? So typically this answer is in radians, okay? And then here, this delta C, again, EIAB is Newton meter Q to the Newton meter squared, okay? Force times length squared. So the units of here are going to be in length. And so in this calculation, the unit's going to end up in meters or length here, okay? And so you get deflection, makes sense, right? Deflection here. Now, the other thing that you also want to remember is what does this positive rotation mean, and what does this positive displacement mean, okay? And I know the simple answer is that positive displacement means it goes upwards. Well, it also depends on how you did your sign convention when you did the moment diagram. So here in the moment diagram, if you chose positive x going this way and positive v essentially going like this right here, then yes, you know, this positive deflection, that's what we initially did right here, is that this positive deflection at C means that this movement up here is actually delta C. It's going to move up. And so the deflected shape of this is like this, okay? Here's this, and this displacement, if I could erase some stuff here from the elastic curve right here. So this elastic curve, due to that concentrated moment at point C here, there's going to be a deflection upwards, delta C. And that positive value indicates this moves upwards. This positive slope, this positive theta, indicates, according to the sign convention that you chose, that this right here is positive theta C. That's this slope right there. I don't know if you can see that, but this, you know, this slope, this rotation right here is at positive theta C. And this orientation, that slope right here, is a positive slope in our XV coordinate system. Okay, and hopefully that makes sense, and that provided some clarity on the conjugate beam method.